Let's turn our attention now to the leaving group. So we're going to look into the leaving group for a little while, and then we're going to do a recap of what we've seen so far based on our discussion of SN2 before we move on to some other things. So the leaving group overall has to be able to depart from the molecule and exist in a stable form away from the substrate, which means that the weaker something is as a base, the better it is as a leaving group, because weaker bases are more stable. So weaker bases are more stable. No, I don't like this. Fuck this. So let's turn our attention now to the leaving group. Let's talk about the leaving group for a little while, and then we're going to do a recap of what we've seen so far throughout our discussion of SN2 before we move on to the other reaction pathways that we want to move on to. So the leaving group, what we saw originally, is the weaker something is as a base, the better it is as a leaving group. This is because the leaving group has to be able to leave the substrate and exist in a relatively stable form away from the substrate. And we've seen, when we looked at acid-base chemistry, lots of ideas relating to stabilities of conjugate bases and using those ideas to compare acid strengths. And from there, we know how to assess whether something is stabilized by resonance or an inductive effect, these types of things, and how to identify weak bases. Some of them we already know anyway. For example, the conjugate bases of things like HI, HBr, and HCl, which are all strong acids, those are all weak bases. So we can look at the effect of the leaving group on the rate of SN2 through an experiment like the one shown here and summarized in this box. So in all of these cases, the experimenters used hydroxide as the nucleophile, and the structure of the alkyl halide that they reacted it with was the same except for the leaving group. So they changed the leaving group in each case. Now, just like we saw before when we looked at the effects of steric hindrance on SN2 reactions, they're keeping the concentrations of these things constant. So in all four experiments, hydroxide ion concentrations started out the same, and alkyl halide concentrations started out the same. So what we see when we compare the rate of reaction, of SN2 reaction in all of these, is that the iodide, the alkyl iodide, reacts 30,000 times faster than an alkyl fluoride. So iodides and bromides, I and Br, are excellent leaving groups. Chlorine is okay, so it's only 200, its relative rate is only 200 to 1 compared to fluorine, but it's still reasonable as a leaving group. Summarized in the table below, the good leaving groups, again, are going to be weakly basic, and we're about to get a better, closer look at this guy, OTS, which is called tosylate, so that's a weak base. And poor leaving groups are going to be things like hydroxide, alkoxide ions, fluoride ions, and then these two, carbanions and hydride. These are very strongly basic. So the weaker something is as a base, the better it is as a leaving group. Now let's take a look at this idea. So let's say we have methyl chloride, and we're combining that with a hydroxide ion. To get methanol and the chloride ion. Now let's say that that's an equilibrium. Now, in general, we can consider any reaction an equilibrium reaction, but in actual practice, not all of them are. Most of them are going to favor strongly one side or the other. But for the moment, let's just consider this as an equilibrium. How would we know which side is favored? Well, remember that an energetically favorable SN2 reaction, this means an exothermic reaction, involves something where a stronger base displaces something that's a weaker base. So that would be the forward direction as this is written. because the hydroxide ion is going to be a better nucleophile than it is a leaving group, and chlorine is going to be a better leaving group than hydroxide. So if we look at the forward direction, that would be the energy diagram shown on the left. So that represents an energetically favorable reaction. The products are lower in energy than the reactants. The reverse of that would be energetically unfavorable. That would be something where you have a weaker base, in this case the chloride ion, trying to displace a stronger base, in this case the hydroxide ion. So the direction of reaction, let's take out the reverse reaction arrow now, the direction of reaction that favors the better leaving group, or the weaker base being the leaving group, is the favorable direction of the reaction. Now, let's say that you have an OH group in your molecule. So you have an alcohol, but you want to use it to do an SN2 reaction. Well, if you just try to attack that with a nucleophile, you're not going to get very far. So let's say in this first line that this is a good nucleophile, and it's weakly basic. In such a case, nothing is going to happen. The nucleophile is weakly basic, so it's not going to be able to displace the more strongly basic hydroxide ion from the substrate. It's also weakly basic, so it's not even going to be able to pull the proton off the OH group. So nothing's going to happen here. But let's say by contrast, you use a nucleophile that's more strongly basic. In this case, it still is not going to be able to displace the hydroxide ion. The hydroxide ion is a poor leaving group. But it will be able to remove the proton from the OH group and give you an alkoxide ion. So either way, you're not going to get any SN2. So instead what you have to do is convert the OH group into something else that's a better leaving group. Now the typical candidates for this are bromides, so you can convert an OH group to a bromine by using a reagent called PBr3, so phosphorus tribromide. This will work on primary and secondary alcohols only. If instead of a bromine you for some reason wanted a chlorine, you could use a reagent, as shown in the second example, called thionyl chloride. And this one is called thionyl chloride. And that'll have the consequence of changing the OH group for a chlorine. And again, this is going to work on primary and secondary alcohols. A third possibility that you can use is to make the alcohol into something called a sulfonate ester, which again is going to work best on primary and secondary alcohols. To do so, you're going to treat the alcohol with a combination of reagents. The one on the top is called tosyl chloride, and the one on the bottom, PYR, is an abbreviation for something called pyridine. We'll look at the structures and the details of this shortly. The result is going to be what's called a sulfonate ester, or sometimes people call this a tosylate. And right here, OTS is your leaving group. Okay, so let's look at the details of the tosyl chloride and pyridine. We're going to do that on the next page, so let's first look at the details of how PBr changes an alcohol into an alkyl bromide. Sorry, PBr3. Okay, so let's start with this alcohol, which you'll notice is not only chiral, but the OH group is attached to an asymmetric carbon. So that asymmetric carbon is going to become important. So here's PBr3. And so when you combine the alcohol with PBr3, the alcohol is going to attack the phosphorus and kick out one of the bromines. So that itself is an SN2 reaction. Notice that nothing has happened at the carbon that the oxygen is attached to. So the stereochemistry there stays the same. So now what you have is the oxygen attached to the phosphorus, which still has two bromines on it. And you have a bromide ion. This is the same bromide ion that got booted out in that first step. Well, now it's going to come back and it's going to attack here and kick out this entire group. So what you have in this yellow circle is a ginormous leaving group. When the bromide ion attacks and displaces that ginormous leaving group, that's another SN2 reaction. And so that's occurring with inversion of configuration. And so because we know that in an SN2 reaction, the nucleophile attacks from opposite the bond to the leaving group, and in this case, the leaving group is directed toward us, that means the bromine came from behind the page. So the result, oops, not an OH, there's going to be a Br there now. The result will look like the structure shown on the right. So the configuration inverts if you use PBr3. If the OH is attached to an asymmetric carbon. Okay, so let's look at a few examples of what we've been talking about so far before we turn our attention to the details of the tosyl chloride and pyridine. So let's say you have this alcohol, which is secondary, so any of these methods would work. If you treat this with thionyl chloride, it's simply going to replace the OH group with a chlorine. For thionyl chloride, don't worry about a stereochemical outcome. A lot of that depends on the solvent that you use, and so that's beyond what we need to worry about. Now, another thing that you can do with PBr3 and with SOCl2 is to treat carboxylic acids. So you can also replace an OH group on a carboxylic acid. So we'll just use acetic acid as our example. So if you treat acetic acid with PBr3, you'll get an acid bromide. And if you treat it with thionyl chloride, SOCl2, you get an acid chloride. Okay, now let's look at the details of tosyl chloride and pyridine. So using tosyl chloride and pyridine with an alcohol allows us to prepare something that we call a sulfonate ester or a tosylate. So that's this guy over here. This is the sulfonate ester or tosylate. Okay, so what are these reagents? Tosyl chloride stands for para-toluene sulfonyl chloride, or TSCl. So its structure is shown here. So what goes on in the reaction is that when you combine an alcohol with tosyl chloride, the oxygen in the alcohol is going to attack the sulfur and displace the chlorine. So as the result of that, you'll get a structure that looks like this. Now this looks similar to things that you've seen before, where you have an oxygen connected to a carbon and some other stuff. The other thing, or what you saw previously, was that the oxygen had 2 protons attached to it and a positive charge. So, for example, when water attacks a carbocation, think of the intermediate there. What happens in cases like that, one of the things that can happen, is that that oxygen then gets deprotonated. And that's the point of having the pyridine in solution. So the structure of pyridine is shown here. Pyridine is an amine, and it's a weak base that's used as the solvent in this case. And so when this intermediate forms, the pyridine is right there to mop up that proton. So then we end up with a neutral compound and all of this in the yellow box is the leaving group. This is OTS. So that's the mechanism of how you would form the tosylate or sulfonate ester. Now, a few minutes ago, we looked at a case where we had a chiral alcohol where the OH group was attached to the asymmetric carbon. So if we start with a similar situation and treat it with tosyl chloride and pyridine, notice in the mechanism up above that the carbon that the oxygen is attached to is not involved in the reaction. So tosylating this alcohol is not going to change the stereochemistry. However, now that we have something that has a good leaving group, presumably we wanted to make it so that we could react it in something like an SN2 reaction. So let's use sodium iodide and acetone as the reagents to treat this tosylate. Now it's been a while since we've looked at a set of reaction conditions, so let's do that here. So first of all, we have a secondary substrate. It has a great leaving group. So this is just about the best leaving group you can have, one of them. And then what do we have over the arrow? We have sodium iodide. So again, remember, we don't really care about the spectator ion. What we care about is the anion part of this, and that's I-. And we've seen from the passes that we've made through the frequently encountered nucleophiles that iodide is an excellent nucleophile. So we have a good nucleophile. And we can also throw in that this is weakly basic. Down below the arrow is this. This is acetone. Acetone we now know as a polar aprotic solvent. Okay, so we have a secondary substrate. Those can undergo SN2 reactions as long as they're not terribly hindered. We have a great leaving group, which has to be the case for any of these substitution and elimination reactions. We have a good nucleophile that's weakly basic. The fact that it's weakly basic suppresses E2. So that makes E2 less likely, because if something's a weak base, it's less likely to accept a proton, which is what you need to have an elimination reaction going on, especially in E2. And then finally, you have a polar aprotic solvent. And remember, you don't have to have a polar aprotic solvent for it to be an SN2 reaction, but it's often a clue. So all of these things together point towards an SN2 pathway. So the iodide ion, let's draw the mechanism. You can never draw the mechanism of anything too many times. The iodide ion is going to attack the carbon with the leaving group and push the leaving group out. Because it's an SN2 reaction, this will go with inversion of configuration, and so the product is going to look like the structure shown on the right. Tosylate ions are the conjugate bases of strong acids. Strong acid is tosic acid, which is something that we've been recently introduced to in the course. Tosic acid has a lot in common with the structure of sulfuric acid. It's a strong Bronsted acid. So this is similar to sulfuric acid. And as such, its conjugate base is going to be exceedingly weak. In this case, it's stabilized by resonance. So this over here is the structure of OTS minus. So that's why it's such a great leaving group. Okay, so what have we seen so far? Let's recap. So for SN2, which is what we've been talking about, that's where we're going to have the most information. First of all, we know that SN2 works best if you have an unhindered substrate. So those will be things like primary, actually, let me do this a different way, methyl, primary, and sometimes secondary. SN2 is also favored by good nucleophiles that are weak bases. So good nucleophiles that are weak bases, so that would include things like I minus, Br minus, Cl minus, HS minus, RS minus, and then cyanide and azide ions. So good nucleophiles that are weakly basic favor SN2 pathways, or good nucleophiles that are basic but unhindered. So that's going to be things like hydroxide and methoxide ions. Larger strong bases tend to give you more E2. We also know about SN2 that an inversion of configuration occurs. When the nucleophile attacks an asymmetric carbon. We know that SN2 occurs through a concerted mechanism. Which is to say it's all happening in one step. We know it has no carbocations in its mechanism, therefore there are no rearrangements. And finally, we know that SN2 reactions go faster in polar aprotic solvents. And the polar aprotic solvents that we've seen: acetonitrile, acetone, DMF, DMSO. E2, what we've seen about E2, that pathway occurs when you have tertiary or other sterically hindered substrates. And E2, in particular, is favored by strong bases, especially if they're hindered. Now finally, SN1 and E1. So we haven't talked much about these at all yet, except to say that these will not be observed in the presence of a strong base. The reason for this is because both of these pathways involve carbocation formation. Carbocation formation is rate limiting. If there's a strong base hanging around, it's going to react much faster than a carbocation can form. Therefore, you'd get an E2 pathway instead of an SN1 or E1 pathway, or potentially you could get SN2. So the base would react faster than a carbocation could form. So that recaps what we've seen so far. We'll turn our attention next to the other pathways.